Hello everyone and welcome back. I am Mr. Cobalt and in this video I want to talk about pressure and how pressure is the result of molecular collisions. And so this is going to kind of help us with our gas laws and the behavior of gases and the properties of gases as well. So I want to start off by talking about pressure in general and then kind of relate that to particles and gases as well. So one of the equation for pressure is related to uh, force and area. So the example I like to use is with regard to like dancing. Now bear with me. So if you have a dance partner and she or he is not a good dancer, um, and they tend to step on your foot. So if I'm dancing with a woman and she's a clumsy dancer, uh, would I prefer that she wear the platform shoes while dancing? Those are like the flat bottom, no heels. Or would I prefer her to wear stiletto heels when she steps on my foot? And so if you give that some thought, your inclination might be, yeah, I would rather have her wear the platform shoes. And I think we all have experience where um, the smaller the object, the more pressure or the pain it's going to have. So if someone steps on my foot wearing stiletto heels that are like the size of a dime or smaller, um, that's related to the surface area of the heel. Now, it doesn't matter how much she might weigh, because if that well, let me step back here. So the force would be related to her weight, right? So the weight, it doesn't matter how thin or how small she is. The fact that the area here that the force, the weight is kind of being centered into or concentrated into is so small that she could be the most petite woman on the face of the earth. If she's wearing stiletto heels, you don't want her to be stepping on your foot because all her weight is going to be concentrated into that one area on the heel, and it's going to hurt because that's a lot of pressure to put on your foot. Whereas a someone who's wearing platform shoes, that body weight is spread out through a larger area, so it's not going to hurt as much. Might still hurt, but definitely not as much if she's wearing stiletto heels. This is one of the reasons why also that people wear snowshoes in areas where there's lots of snow and it's deep, and maybe the snow is not as compact. So snowshoes have a larger area so that your body weight can be distributed evenly throughout the area of the snowshoe, and that's going to keep you from falling through the snow. And in certain areas, you don't want to fall through the snow because if you fall through the snow, you're not going to be able to get out, and it could be a health or life issue here. So this is how force and area are related to pressure. So the larger the force, the larger the pressure. The larger the area, the smaller the pressure. So if you decrease the area that the force is acting on, then the pressure is going to go up. If you increase the force that is acting on a certain area, then the pressure is going to go up. Okay, so that's how pressure is related to force and area. Now, how does this relate to particles and gases? So if you have particles that are moving really fast, right, they're going to be hitting the sides of the container with a certain force. So think about if I have a baseball and I throw it up against the wall. It's going to hit the wall with a certain force and then bounce off, right? So at the moment that the ball is in contact with the wall, it's applying a force during the contact, okay? So the particles are the same way. So if the particles are hitting the sides of your container, it's going to put a force on the sides of the container while it's in contact. And then when it's off, it's not going to have the force anymore. So if you think about all the particles in a gas, so if you have a balloon, for example, and you have a certain amount of gas in the balloon, those gas particles, there's many gas particles in the balloon, and so they're all hitting the sides of the balloon. And if you took a snapshot of the particles at any one moment, you would see that at any one moment there's going to be a number of particles, a huge number of particles hitting up against the side of the balloon. Now the balloon has a certain area, or any container has a certain area. It's called the surface area of the container, and that's related to the volume, right? So, so depending on the surface area, right, that the particles are hitting up against, and depending on the number of particles that are hitting up against the side of your container at any one moment, that's going to determine the force. So if I put more particles into the balloon, then I'm going to have more of a force acting on the side of the balloon, because at any one moment I'm going to have many more particles hitting up against the side of the balloon. So same way, if I take particles out of the balloon, then there will be less particles in the balloon, and then therefore there will be less particles at any one moment. If I take a snapshot, there will be less particles pushing out on the sides of the balloon, right? So even though the surface area is staying the same, the force on the balloon is going to go down because the number of particles hitting up against the force. So the force of the gas is going to depend on the number of particles that are in the container. It's also going to depend on the size of the container, right? You increase the size of the container, you're going to increase the surface area of the container as well, and that's related to volume, right? So if I increase the size of the container and I keep the particles the same, then I would expect that if I increase the size of the container, the area is getting bigger, right? And so the surface area gets bigger. And if I keep the number of particles the same, well, the force that the particles are hitting up against the side of the container is going to stay the same. So that would decrease pressure. So I would expect pressure to decrease. If I keep the volume the same, that means the surface area stays the same. But if I put more particles into the container, then I'm going to have more particles hitting up the side of the container, and that's going to increase the overall force of the gas, and that's going to increase pressure, right? So we know this from like inflating basketballs or volleyballs or whatever sport you want to think of that has a ball. If it's not very taut, right? So if it doesn't bounce very well, then you put more air into it. What happens when you put more air into it? It gets more pressure. You could feel the pressure build up inside the ball. That's because you're increasing the number of particles, and the number of particles, more particles are pushing up with a certain force, so the overall force increases. Now, there's one thing I want also to bring in as well. This idea of temperature. So temperature is going to be related to speed of particles. So if we remember, temperature is related to thermal energy. Thermal energy is related to the speed of the molecules. So here, if you increase the temperature, then you're increasing the speed of the molecules. Now, think about what happens when you increase the speed of the molecules. So take my baseball example. So I throw a baseball against a wall, and it hits with a certain force, and it bounces off. Now, what happens if I throw it harder and faster, right? So I throw the ball harder and faster, hits the wall at us. It's going to hit the wall harder, right? What's going to happen to the force that's being applied to the wall by the ball? It's going to go up, right? So the speed of the ball hitting the wall is going to determine the force that is applied or to the wall while in contact. So think about that in terms of the gas particles. So if I increase the temperature of the gas, that means the particles are going to move faster. If they're moving faster, then that means they're going to hit the sides of the container harder. And that means the force that's put onto the sides of the container is going to go up. So if I have a can and I put more particles into the can, the pressure will build. But if I keep the particles the same, but I raise the temperature of the can, right? So if I have an aerosol can and I throw it in a bonfire, right? The particles, the number of particles in the can stay the same, but I'm increasing the temperature of the particles, and the pressure goes up because the particles are moving faster. They're hitting the sides of the container harder, and so the force goes up, even though the area stays the same. So as the speed increases, as the temperature increases, the speed increases, the forces are going up, and the pressure is building until it explodes, and the integrity of the can is compromised. So this is a kind of an introduction into how the pressure is related to the speed of the molecules, the number of the molecules, the area of the container, the volume of the container, and things like that. And this is going to be very useful for understanding the gas laws. Now, there's a few things I want to point out. That these are equalities between different measurements of units of pressure, and these you need to know so you can convert between different units. So 1 millimeter of mercury is the same as 1 torr, right? Torr is the name of one of the scientists or people that was involved in this, and so they're kind of just naming it after him. So 1 atmosphere is equal to 760 millimeters mercury, which is equal to 760 torr. You have 1 atmosphere equals to 101,325 Pascal, or 101.325 kilopascals. So these are all equalities, and the reason I have these here is so that you know them, and that you can use them to then make conversion factors. So you need to be able to convert between these units, which is the upshot of what I'm trying to say. So where does this idea of the 760 millimeter mercury? Well, that comes to this here. This is a barometer with mercury in it. And so what you can see from the barometer is, here's the mercury. You have a pool of mercury, and this was an empty tube. And the air pressure is pushing on the mercury from here, and it's causing the mercury to go up into the tube. And so now there's going to be a balance between the weight of the mercury column here and the atmospheric pressure. So this is going to go up until it stops, and at that point the weight of the height of the mercury column is going to be equal to the atmospheric pressure, whatever that is. And that's how a barometer works. So the height, this is where we get our millimeters of mercury. So what they're saying here is 760 millimeters of mercury. If this was 760 millimeters of mercury, that would be equal to 1 atmosphere of pressure. Okay? So that's really all I wanted to cover in this video. I hope this is helpful, and we're going to go over the simple gas laws and things like that, and in later videos. If you like this video, please go ahead and like it, subscribe to the channel, and share the video with everyone. Make a comment in the comment section and let me know what you think, and ring the notification bell so you can be notified of any other new videos I put out. Thanks for joining me, and I'll see you next time.